Alright, this is going to be CCNA 3, Chapter 3, lecture on Spanning Tree Protocol. That's what STP stands for last time I checked. So yes, Spanning Tree Protocol, that's what we're doing. It is going to be used, it's a Layer 2 protocol used to determine the best path for your frames to travel. Okay. We have things like OSPF, EIGRP to determine where things go when they're routed. But we do need something to determine a best path when in turn it comes to layer 2 traffic as well, your frames, to avoid certain problems that will occur. Okay. So we're going to look at spanning tree concepts, the different types of spanning tree protocols that do exist, as well as how to configure those spanning tree protocols. So that's what we have coming up. We'll see how long this takes us. I don't think it'll be too long of a video, but I can't make any promises. So let's see what we've got. Spanning tree concepts. What are we trying to avoid? Why do we use spanning tree protocol? It is going to be used because, well, one thing that's going to happen is you get a continuous loop of traffic along your network. If you have more than really 2 switches, we got 3 switches or more, you're going to have the potential without STP of what's called a broadcast storm, which causes MAC database instability. What basically is going to happen is you've got PC1 down here. It will send a frame to S2. Let's say it's a broadcast frame to S2. S2 broadcasts that out to all of its ports except the ingress port, which is fine at first. It goes to S3, S1, all the PCs down here. But as it goes to S3, S3 receives this broadcast and says, okay, I've got to broadcast it out, everything but the ingress port 2. I'm going to F1 to S2, S1. S1 receives it. It's already received a frame from S2 and broadcast it to PC4. But it's going to go ahead, since it sees it's a broadcast frame, and forward it out. Okay? And then shoot that back down to S2 as well. So when S1 receives the broadcast frame, it goes out both ports. When S2 receives it again, it's going out all of its ports once more. And back up to S3. S3 goes to S1, S1 goes to S2, broadcasts it all out, S3, S1. So you get this broadcast storm. That's the storm. You just have a frame continuing to circulate around your network endlessly pretty much. So we're trying to avoid that with STP by having just one best path for your frames to travel along a network. Along with that storm is going to be some MAC address database instability, because you're going to constantly have your switches receiving frames on their ports, and that can cause, well, instability in your MAC database. Okay. So that's what we're trying to avoid. I believe we have another example of that here. So it's just talking about the same thing we just did. You want to avoid this storm of frames being sent along your network. Okay. So your spanning tree algorithm introduction, how it calculates what is the best path, how your switches are set up to designate a best path. Basically how it starts with something called the root bridge. Your root bridge is going to be a switch that is set up as kind of like the central hub for decision making. All your other switches are going to make decisions based on how quickly they can get to that root bridge. Okay, let's take a look at a root bridge. So here, you do have a root bridge. This switch here, how do you designate a root bridge? There's something called a bridge ID that is, by default, it's going to be the same for all switches. So if you don't go in and change the ID on any switch, what's going to happen is the switch in your network with the lowest MAC address is going to be designated as the root bridge. So that can be kind of random. So if you want to make sure that you have a switch of your choosing set up as the root bridge, you're going to need to set that bridge ID, which isn't the hardest thing in the world to do. There will be a command for that coming up. Okay. But anyhow, here's our root bridge, which is kind of the central hub for our decisions to be made on. Okay. A designated port is any port that is on the other side of a root port. So maybe I should start with what a root port is. A root port is the port that has the shortest cost from a certain switch to get to the root bridge. So on S2, its lowest cost to get to the root bridge is the link that goes right to the root bridge. Same thing with S3. These are both root ports. Okay. Anything on the other side of a root port is a designated port. So basically, all of your links on your root bridge are designated ports by default. They're going to be because they're directly connected to the switches across from the root bridge. Okay. So that's what you get with the root bridge. All of those ports are going to be designated. All right. Over here we have some ports that are not desirable. They're not close to the root bridge. So what you end up with is an alternate port and a designated port down here. That doesn't seem to make too much sense, but there's a reason for it. We are killing this link effectively, or killing this path, by having one alternate port. You can't go through there, so traffic's not going to travel that direction. But if this link were to go on down trunk 1, for instance, you will need to use trunk 2, and trunk 2 can be brought up into a forwarding state faster if you have one designated and one alternate port, because you only need to change the state of one of them rather than changing the state of both. So that's going to allow the forwarding process to occur more quickly. That's where you'll see an alternate port and a designated port here. We'll talk about why or how we make the decision as to which port is the alternate and which is the designated in just a moment. So we'll take a look at that. Again, your root bridge serves as a reference point for all STP calculations, or the central hub, if you want to call it that. That's what I've been calling it. The switch with the lowest bridge ID, I want to say Bluetooth ID, the lowest bridge ID becomes the root bridge. And again, those bridge IDs are the same by default. Okay. You've got your root path cost. You can see what cost is assigned to each link based on speed. Okay. If you want to tweak that, you want to make sure one link is preferred over another, you can lower the cost yourself on a link. Just go ahead and go spanning tree cost and give the value of the cost that you want. Okay. Do it on both ends of a link. Make sure the cost is low, and you're sure that that link will be used. If you, for instance, use a 1 on each side, for instance, that link is going to be used. So if you want to, again, have some more control over your network, you don't want to just allow things to happen based on link speed, which isn't a bad thing, you can do that spanning tree cost command if you'd like. And if you want to see the root path cost and the verified your port and your internal root path cost, you can do show spanning tree, and if you set any custom cost, you would see that, or you just see the default cost that was there if you left everything alone. So you have that option. Okay. Rapid STP is what RSTP stands for, and how your ports are assigned. We talked about this a little bit, but let's go over it again. Your root bridge automatically configures all of its ports as designated or in the designated role. Designated ports are configured for all LAN segments. Switch with the lower cost, the blah 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 blah. So what I didn't talk about is that, or maybe I did. I can't remember. It's a whole 8 minutes ago. Each switch makes its own calculations based on what to determine which port's going to be a root port and which port's going to be a alternate or designated port. So that's all done on a per switch basis. Okay. So here's a little bit of an example. So what we've got here is you've got your root bridge, you've got a couple other switches here as well. Okay, all of your ports on the root bridge are going to be designated. All right. S2 determines that, okay, to get to the root bridge, again, that's what we're trying to get to. That's what we make our decisions based on. To get to the root bridge, I go through F01. Okay, and that's my root port. So that's going to be your root port for S2, S3, F01 also goes to your root bridge. That's your root port. Then we have this link here, which is going to be disabled to an extent. It's going to be put into that alternate state where it's not going to forward traffic. All right. So how do we determine what's going to be a designated and what's going to be an alternate port? Is, well, based on your bridge ID or your MAC address, depending on which one's lower. If your bridge ID is lower on one, so S2's bridge ID is lower, that side of the link will be the designated port. The one attached to S3 would be your alternate. Okay. If the bridge IDs were equal, then we go to MAC address, and the lower MAC address, this would be designated. That would be alternate. So that's how they determine it. It's not the biggest decision in the world. Again, as long as one is designated, it's going to help that process of switching back to a forwarding state occur a lot quicker, and that's the main concern. So I don't think you would really go in there and change the bridge ID or MAC address costs there, but you could. You can change the MAC address. Well, I guess if you were really determined, you could. For all intents and purposes, you can't change the MAC address. You can change the bridge ID though if you wanted to tweak that. Okay, and back here we go, and down. Your bridge protocol data unit frame format. You can see the different fields here. The ones we kind of talked about: the root ID, the root path, cost, bridge ID, port ID. That's probably your most important information. Otherwise, you've just got your message age, your hello time, protocol IDs, things of that nature. So probably not the most important information other than fields 5 through 8. Your bridge protocol data units are going to be sent every 2 seconds. Contains information about its own bridge ID, the root ID, and the root path cost. You've got an extended system ID down here, which does include your bridge priority, and your default is there. Your extended system ID, which contains VLAN information and your MAC address. Okay. So you've got all that information in your extended system ID. Just note that. And we're on to the next section. So on these varieties of spanning tree protocols, we have a few different ones, 5 to be exact, and they are STP, PVST plus, RSTP, Rapid, PVST plus, and MSTP. They don't sound very good, do they? Sound like, anyway, we'll continue on. Spanning tree protocol is our legacy one, pretty much. You're going to manage your entire topology, LAN with STP, regardless of VLAN. So there's always going to be one root bridge. There's going to be set paths for all traffic to follow on STP. Okay, things change up with PVST. PVST is going to allow you to manage a root bridge per VLAN. So in a topology, you could have one root bridge for VLAN 10, another root bridge for VLAN 20, so on and so forth. So they could all have separate paths that they're taking with PVST because the bridges are set and the paths are set per VLAN. That's going to help you with load balancing. So if you want to use one link for a certain VLAN, another link or another path for another VLAN, you're going to have your traffic spread out across your different links, which can be kind of nice. You can see the resources needed are going to be a little bit higher there because you are going to be having more traffic on your network, more bridge protocol data units sent across the network. So you'll need to have more bandwidth and more processing speed in order to handle all those processes. Okay. those are both slow convergence, the top two, because there's 5 different states that your ports could be in, and they need a transition between those states being blocking, learning, listening, forwarding, and disabled. Okay, so those are the different states that you'll see in RSTP and rapid PVST, which is the R stands for rapid in both these situations, just rapid there and rapid there. Your convergence is going to be a lot faster because there's only 3 states, which are blocking or inactive, forwarding, and disabled. Okay, so you can go right from blocking to forwarding pretty much in these rapid states. In order for that to happen, you're going to, again, need more processing power, so your resources needed are going to increase. We went from low to medium in STP. We go from high to very high in rapid PVST. Same things still apply. You've got, for your Cisco proprietary, the PVST, that's per VLAN, and your universal protocol STP and RSTP, all VLANs. So you're only going to have, again, one root bridge there on RSTP. You can have multiple root bridges on rapid PVST per VLAN. Okay, so you've got that. And the last one here, MSTP. This is what you're going to use if you have multiple VLANs and you want them all to use the same path. You can take all those multiple VLANs and they will take the same path through MSTP, basically taking that group, setting one root bridge for them and all the same paths through the network by setting up this MSTP protocol. Okay, so if you want basically all your VLANs to take the same path, MSTP can make that happen. Okay. So PVST plus, we just discussed how it's different from STP, is that you can have a different path for each VLAN in your network. So you could have, let's see what they got here, VLAN, root bridge for VLAN 10 here, root bridge for VLAN 20 separate, and you're going to issue commands that involve the VLAN name in order to set those root bridges. Okay, from setting either a unique BID, bridge ID, or just you can straight up say, hey, this is my primary root bridge, and then we're going to talk about something called the secondary root bridge, which can kick in if your primary root bridge fails. Okay, so again, PVST Plus allows you to have multiple root bridges per, or separate root bridges per VLAN. Okay. Again, we discussed briefly the different states that a port could be in. If you're using STP or PVST Plus, those states are consistent between the two, which are blocking, listening, learning, forwarding, disabled. Okay, and we'll talk about what each one of those are. The blocking state means that you're receiving bridge protocol data units, but you're not forwarding them, you're not forwarding traffic, you're just receiving them, and that's it. Your port is not forwarding traffic, it is not being utilized. Okay, if you're in a blocking state and you receive a protocol data unit telling the port that it needs to become active, then that port is going to go into a listening state. Okay, the listening state is where the port is looking for the path to the root bridge. While it's listening for the path to the root bridge, then it's also beginning to forward protocol data units, bridge protocol data units, informing the other switches that that port's about to become active and participate in the forwarding process. Okay, so that's listening. Learning is when you're learning MAC addresses, the port is learning MAC addresses in the learning phase, and then finally, after it learns its MAC addresses, it goes into a forwarding state, which just means it's forwarding data, it's participating, basically going from an alternate port to a designated port. if you remember us discussing that a little earlier in the video. Hopefully you do. Okay. And then, disabled. So there's that. Okay. Extended system IDs ensure switches have unique bridge IDs for each VLAN. Again, the extended system ID does incorporate your MAC address, so that is going to make each one of them unique because your MAC addresses should be unique. Okay. I believe we talked about in order to manipulate which switch, to determine the switch that will be the root bridge, you can lower the bridge ID, okay, or you can just go ahead and assign it. There's a command to assign a switch as the root bridge if you don't want to have to lower that bridge ID. So there's those two options for you, and we'll talk about those commands in just a minute. So rapid PVST is again per VLAN RSTP. Okay. Both of them, rapid RSTP and rapid PVST, can achieve convergence much faster because they are using Type 2 version protocol data units, and the flag byte in those basically allows the ports to go from a blocking state to a forwarding state without going through the listening and the learning. Okay. Which brings them up online and has them participate in topology a lot quicker, allows the topology or the switches to detect a failure in a link and make an adjustment, so other links come up a lot quicker. So it's really this flag that's key in the faster convergence. All right. In order for those ports to be able to be brought from a blocking state to a forwarding state that quick, you are going to need more processing power. So you saw on that chart that we had on the screen before that you do require more resources to make rapid PVST or even RSTP happen. Okay. Through RSTP, you have something that's called an edge port. And an edge port is basically a port that does not connect to another switch. It connects to a router, it connects to a server, it connects to a PC, an end device. You can see in this graphic here, we've got those ports labeled. And those ports are going to be set up, they're set up to forward data immediately because they're always going to be forwarding data. They're not part of the decision-making process as far as which path to take. These paths are always going to be taken if you're going to the database, the PC, or whatever. In order to make that happen, there's a command called port fast that you need to issue. I believe we'll see it a little later on. I'll make sure we say it a little later on. And that puts you into a forwarding state immediately. Okay. You've got two link types with rapid PVST. Point-to-point, the most typical. In fact, shared you won't see as much because you'd have to have a port operating in half duplex mode that connects to a hub. We don't really even use hubs much anymore. We're going to be using switches in almost all networks. It'll be rare that you see a hub, but you might. So that's what shared is there for. There's a command that allows you to turn a port into a shared port. But the rest of them are going to be point-to-point. Okay, you can see that the only short port here would be the one going to the hub here and then going to the router. Okay, root ports and alternate backup ports do not use the link type parameter in most cases. Designated ports do use that link type parameter. Okay, so we've got that there and we're getting closer, ever closer. All right, spanning tree configuration. How do we set this all up? Let's take a look. So here we have the configuration of PVST plus, setting the root through two different methods. You can have a root primary command that will set up whichever switch you're configuring it on as the root bridge. Okay, you can have a root secondary command that will set up a switch as your backup root bridge. So those two commands kind of go in line with each other. Also, the other method you could use is the lower bridge ID. Okay, so you go to priority, put in the priority number, the lower the better. So if you want to make sure that a switch is configured as a root bridge, you could lower that ID. Okay, lower that priority. Okay, so if you do that, it is essentially lowering the bridge ID so you can have your bridge selected. I forget what the default is, somewhere around 36 or 3700 something for your switches. So if you lowered it to 24576, then you would have the lowest bridge ID, and that's going to be elected as your root bridge. Okay, so you've got that. You've got show spanning tree, and what that's going to show you is something like this. If you are not the root bridge, okay, you would see your root ID, and that would show you what the root bridge's priority is and everything. You've got your bridge ID, which is you, and this switch just so happens to be both. So you could see different values there. Okay, you can see the ports on your switch, what state they're in. Are they forwarding? Are they designated? Are they root? Are they alternate? What are they? So those are all there if you do your show spanning tree command. You've got your port fast commands. We talked about that with your edge ports that are connected to computers or connected to servers, things of that nature. You've also got your bridge protocol data unit guard that enables. Why? Or what you would do that on a port fast port, and why is because if your port is assigned to port fast, or you issue the port fast command, then you should not be receiving bridge protocol data units anymore. Okay, that's part of the port fast command. If you do, that means a new switch could have been introduced or something wrong is going on in your topology. Okay, you got some new item that could be creating problems, could be creating a loop in the network or a loop in your topology. So what this bridge protocol data unit guard enable does is if your port fast interface or your port fast port does happen to receive a bridge protocol data unit, which it shouldn't, then that port will go into an error disabled state so as not to create a loop or anything of that nature. Pass along any bad information. So that's what bridge protocol data unit guard does. It's going to error disable that port if it receives a bridge protocol data unit. Okay, and again, you do that on a port that you've already assigned port fast to, and you can see those commands down here in action. We talked about load balancing and using different switches as root bridges for different VLANs, and you can see an example of that here. For instance, switch 3, we're going to use that as the primary root bridge for VLAN 20, and switch 1 you're going to use as the primary root bridge for VLAN 10. And then they're the backups for each other as well. So you'll have traffic moving along different paths for the different VLANs, utilizing all of your link speed, creating some load balancing in your network. So that's what we have here. Here are your commands for setting up your switch to support or activating rapid PVST on your switch. So you'd go spanning tree mode, rapid PVST. That puts your switch into rapid PVST mode. You can then go to your interface, make the spanning tree link type, whatever you need to make it point to point. In most situations, we talked about that you only use the shared one if you have a hub, pretty much, and we don't have hubs very often. You really don't have to set this link type to point most of the time, because most of the time you don't have shared ports as well. Then your last step, you're going to clear your spanning tree detected protocols so that rapid PVST is being used. All right. Whoops. Okay, we'll go there first. If you're having issues and you want to take a look at the state of your ports and whatnot, you've got Show Spanning Tree, which will show your STP status for all your VLANs on a switch, or you can do Show Spanning Tree VLAN and then the VLAN number if you want to see just that VLAN. So those are some commands that will allow you to see what role each port is and which state it's in, so you can troubleshoot issues. Okay, two types of STP failures might block ports that should be in the forwarding state, might move blocked ports into the forwarding state. Okay, so basically it's in a state it shouldn't be in. What are you going to do to fix it? Remove redundant links until all loops are eliminated. If you put them back in, it could trigger a new broadcast storm. Before restoring your redundant links, determine and correct the cause of the spanning tree failure. You can do that with your show commands that we just took a look at. Carefully monitor the network to ensure that the problem is fixed. So, got all that there, and then we've got switch stacking concepts. We talked about stacked switches in CCNA 1. Sure, I'm pretty sure. So they basically, for all intents and purposes, act as one switch. One of the switches controls the operation of the stack, and it's called the stack master. It has a single IP address, including passwords, VLANs, and interfaces, so it really is acting like one big switch. Okay, connected through these stack-wise ports down here. All right. Ability to add more switches is a benefit, and all those switches would fall into one single STP instance. They won't be treated as separate switches. The maximum is 7 switches if you're going to be using default STP timers, if you're going to be using stacked switches. So that's what you got, and that's what we got for Chapter 3. So that's a little bit on STP, the different versions of it. Hopefully that video helps you out, and we should be back next week with Chapter 4.